Bear with me. All right, so we are live. All right, so Open PLC or PLC Open was referenced to us as a good organization to reach out to relative to approaches they've taken to define how to interface with various types of other hardware, so to speak. So I reached out, I just went to the website and kind of cold reached out via email. And Eelco van der Wal was kind enough to reply, and then through a couple emails agreed to share some of their experiences in developing of interfaces and defining some of the semantics relative to maybe how they've approached it or defined an interface standard. And so with that being said, Eelco van der Wal with PLC Open has agreed to share some of their experiences with us relative to their project. Eelco, the floor is yours.
Okay, let me.
I will stop sharing.
Share my screen. Is that possible here? Let me see here. Okay, share. Okay. Do you see my screen?
Yeah, it looks great.
Okay.
Presentation mode would be the only other recommendation.
Shall I put it in presentation mode? Does that work?
Hey, yep, that looks perfect.
Is that good?
It looks good.
Okay, first of all, some words to us. We are a worldwide organization. We've got a couple of offices. We are here now for 30 years. So this year we become 30 years. And during that time, we developed a lot of issues that you see here. And I will show you some of those. Now we are, the title, the work group here is hardware interface. We don't look to hardware interfaces. We wrap them up in a software interface, and we do that with logic, motion, and safety. And we focus to the software part. And on top of this one, we do the communication exchange and training parts. If I go too fast or you have questions, just interrupt me. That makes it much more suitable for me too. So let me start with the motion control, because that's probably closest to what you guys are doing. When we started to work on motion control, we had well over 100 different dialects with different architectures. There were no commonalities. So nobody could reuse its knowledge in that sense. Yeah. So what you saw also with the traditional mechanical designs, there was one big motor and you had all kinds of couplings there, mechanical couplings and mechanics. Well, everything that uses oil will wear and tear. So we came up with different aspects there. There are a lot of part there. And what you saw there, you go from a mechanical solution to a control solution. Nothing really new nowadays, but the big changes, of course, that you get from a mechanical construction to a software solution. And so the controller needs software, and we want to create software that is reusable. And that means also if you share it over different platforms, you have different suppliers, and they all want to support the same functionality. You have to take care that you get to a certain level of abstractions. And that's the part where we come in, and that's the part where we set some standards. And this abstraction we do via a thing what we call function blocks. They are not, well, think about it as an object. They are a little bit different, but you have inputs on the left. This is a graphical representation. You can do it in structured text too. You have your inputs on the left with the data types and the names. You have the outputs on the right with the names and the data types. And of course, the function block has a name. And internally, that maps to either via an interface to an intelligent drive motor encoder, or if you thicker interface, then you do with both with modulation directly to the drive motor and encoder. Nothing really new, but this is the encapsulation information hiding. And based with that concept, we identified a lot of function blocks. And one of them is a move absolute. So you see the name on top. Again, this is a graphical representation of it. You see the inputs on the left with the data types. You see the outputs on the right with the data types. There's one difference, and that's this axis rep that goes straight through. That means that it is, in this case, a var in out, like we call it. It's both var in out. So what you see on the inputs, those are the common terms. velocity, acceleration, deceleration, jerk, so nothing much more there. Axis ref as far and out is that means that the structure, axis ref structure, the link to the axis itself is outside of the function block. So you reference, it's a reference call. And the nice thing about that one, you got somebody conversion to the interface, to the drive, and there's a task manager who says this, we do this every 250 microseconds or whatever. And the nice thing is, if I add a second function block to this construct, it refers to the same axis reference and so to the same drive, to the same motor. So you can write a program on top of it and access the thing underneath. Although you probably, from a programmer's perspective, you don't know if there's this network here. I'll go one step back. If there's a network, intelligent network, or there you have built with modulation or any other architecture there. Yeah, so that's the basic idea. It makes it completely independent in that sense. Yeah. Every function block has an error and an error ID output. And the error ID normally you link to it's a word output. You link that normally to a table that gives you a text. So does the conversion to a language. Can be Chinese or English or whatever you want there. That's why we have a word. In this philosophy, we created a whole suite of specifications. There are now, this is an older slide, but there are well over 30 companies and we are well over 67 products. That means that the move absolute on all these implementations for the user is the same, for the programmer. He uses move absolute. He can create his program with these function blocks without having to know on which supplier it will run, on which network it will run. Will it run on a controller? Will it run in the drive itself? So that is this abstraction that we have in that sense. And via the axis ref, you can refer to the relevant data what you want to have with a read and a write commands, and it gives you the right value, although you do not have to know the structure of the axis ref itself. That's not so for the programmer. That's not important. You want to access to the information, to the data in that sense. You want to know how fast it is. You want to set a new position there. So based on that one, we in part one, we did a whole set of administrative and motion related function blocks for single axis and multiple axis. There you see the move absolute and the home and the stop, and you see the cam in, cam out, gear in, gear out. With part two, which is now integrated after the update to version 2 in part one. So it's not so separate, but you see the same structure, single axis, multiple axis, administrative and motion related parts. Part 4, coordinated motion, I will say a little bit more on that one. This is where you build a group and you set the coordinate transform, and you set in this case the kinematic or the kinematic transformations, the coordinate transformations. And that means that you start moving with a group. Think about the robotics, like you guys are very used to in that sense. You have the coordinated motion, so you build a group of axes, like I said, but you also can synchronize such a group, either to a moving belt, for instance, to a single axis, or you can put it the other way around. And I will show you an example there. So that's done by just a function block, so just an entity, you get it all done. Part 6 is fluid power. There's a more limit and load controls. For fluid power means that if you have a heavy machine outside on land, you're moving earth or things like that, and you're moving too fast, you can flip over. There's this limit load and limit motions. Part 5 are the homing procedures. How do you home, and how do you know where you are? And there's different procedures to know where your home position is per axis or per group. And part 3 are the user guidelines, where we show examples in the how you can use this and how you can create the different programs with the different languages and with the different function blocks. So this is an example of a program. You have 3 move velocities working on the same axis. It goes right through the function blocks. If you set the execute at K with velocity 10, and when it's in velocity reached and L is set, you set an execute with a velocity to 20. So the axis moves with velocity 20. And when it's in velocity and M is set, you set velocity 0. So it goes to standstill in that case. Relatively simple to read. For simplicity, I took out all the other inputs and outputs. Yeah, this was a ladder diagram. It looks very much the same if you do it in another graphical programming language, function block diagram. But there you see the ends and a little bit more clearer, but you see the axis going through. You see the 10, the 20, and the 0 at K, L, and M. This is a gear in function blocks where you have a relation between the master and the slave axis. They have a ratio numerator and denominator, so you can set all kinds of ranges that you cannot do in a mechanical form. Acceleration, decelerate, jerk, error idea, and you get the in gear when it's really in gear. It can take some time before the slave follows the master. Example here in the graphical form, I got a first gear in and a second gear in. You see the master is the same in both function blocks, the slave is the same, but you see that the ratio is different. I combined the numerator and denominator, so ratio 1 and ratio 2. So if I execute the first one, it will move. To execute the first one, it will take some time before it's in gear. And if I execute the second one, it will change the ratio, what you see at my slave velocity at the bottom. First, it goes to the same, the slave follows the master in a one-to-one relationship, and after with the second function block, it's twice as fast. So you switch gears with these simple function blocks in this case. And like I said, it's very abstract, but to the programmer, to the user, this is very easily to do. The startup procedure with us with any drive. So if you try to test your drive, motor drive, encoder combination, this is the simple startup procedure. You do a power on that initiates your drive. You do a home if you need a homing sequence, or you know the position already because you have an absolute encoder. And then after that, when you start moving, you move absolute, and then you will see that the motor and drive should go in the right direction in that sense. So this is easy to program, it's easy to test, and it doesn't mention anything about the settings for the network underneath that should be covered in the implementation of the function blocks by the supplier. So if there are different networks there, meaning that should be included in the whole startup procedure automatically. That's our philosophy there. Coordinated motion. Oh, this is where you guys come in too. We go there from the single axis, we build a group, and on the left you see that with this group we start moving, and we got an axis coordinate system, a machine coordinate system, and a piece coordinate system. So the different coordinate systems that we think in, and with that one you can start moving the robot with the commands that you already saw in that sense. And with the synchronized motion, there are several items. So I got an axis group, and I either can link it to a single axis. So the single axis can be the master, or it can be the slave, the axis follows, or I can synchronize an axis group to an axis group. There are some examples there. I'll show you. This is a famous one where you got your robot, and the velocity of your TCP, the tool center point, is related, is coupled to the movement of the motor that is driving the glue out of the end point. So if you go to the corner, it slows down. and that means that you need less glue there too. So you got a relationship between the master being the TCP and the slave being the motor on the tube with the glue. Here you want to synchronize to the axis in the press. This is a press where you put the material in on the left and you put it out on the right. You want to synchronize there. Tracking is where you synchronize to a belt. So imagine that I put a cake on the belt and I ordered online that there should be a name on it of the people. If it's my birthday, there would be my name on it. And so this is then synchronized in that sense that while the cake is still moving, I can make a construction that I write this name on it because I track basically the cake itself. The rest is the movement on top of that one. So what we do is these function blocks is we do an encapsulation there of the functionalities that are inside, the linking to the axis, the linking to the network. And with these basic function blocks, you can create your own higher function blocks, higher functional blocks for cut-to lengths or labeling in that sense. So you can create a library of function blocks which have functionalities that are dedicated to your, or more close to your application area in that sense. So we always advise the users, the programmers, the machine builders in our case, to create these higher level function blocks and create a library of them. And that means that on the bottom, we have, for instance, the motion function blocks. And with that one, you create, in this case, it's a packaging. You see the cutting, sealing, filling, and capping of your packaging lines. And so create your user-derived function blocks there. And we have tools, we have guidelines on how to create those. We normally see some kind of state machine on top that tells you how to stop and start the machine and where it is. What we, okay. So we got a suite of specification there, a suite of suppliers. This is very broad implemented. Part 4 also defines an interface to the part 4, I can do two things. So with the coordinated motion. One is I can run the whole program, including the kinematic model in the controller itself. The other option is that I see it as an interface to look to a robot controller. So outside of the controller is a second unit, let's say the robot controller, and the robot controller controls the robot. And in order to start that moving, you use the commands like set in the coordinated motion being part 4. We are now working on that one to extend it. That's because there's a lot of input from, let's say, the largest 15 robot suppliers in this world to make this interface better, to better tune to their world, I would say. Yeah. So you will see in, it will take some time, but there is an update coming up. Yeah. And that is in this case particular focus to the interface between the controller for what should I say, the plant controller or the production line controller and the robot controller. There can be one or more. The idea is that we will standardize the access to these different vendors in that way. So you can switch robots or you can switch controllers, or otherwise said, you can integrate them much easier in that perspective. Yep. We added safety. This is just another interface. How do you deal with that one? So safety is for the personnel safety. Also there were too many dialects, too many standards. But you need to be with the governmental requirements, let's say the law, you need to make sure you run that. So what happened with going from a mechanical solution to control solution is, of course, you get more servo drives on the bottom. more drives, more motors means that from this master, this one motor, where you have got your hardwired safety functionality, you get now the problem. You have so many drives that you see a safe network coming in that can be separated from the whole, let's say, the network to motion drive profile. The next step, of course, was that you combine it. So you use the same cable and you have those. Of course, the next step is you add the safety controller to there. And based on that one, we created a whole set of function blocks again, and more than that, a limitation in the programming languages to make sure that you can easily add your safety application program to your machine, to your environment. So that's the basis for easier commissioning, because these function blocks are already approved by TÜV or any other organization there. So we standardize the functionalities, and that means also that the training part is much easier. Just to show you an example there. Oh, I don't think I added the example. Okay, we got a suite of specifications there too. And one of it is, of course, is also the safe motion in this case. We have, of course, a separation between the functional application on the bottom and the safety application on top. I can read the data, but sometimes I can exchange the information between both. So we are working on creating the safety application with the higher level function blocks there. Another interface that we have provided is the communication. We use OPC UA there. We joined the OPC Foundation. Jointly, we worked on these specifications. OPC, in a sense of client server, defined how you communicate in an application session over a secure channel. And in this case, we define what you transfer, in the sense that we do the profiles there. And that means that we map those two worlds. I'm not sure if you can read it, but on top is more, let's say, the object oriented, and on the bottom is the different entities that you have in the controller. And we map those models to each other. And for that one, we created, this is the software model part, but we also created function blocks to become the client. So the client talks to the server. The server, in our case, is based on the software model, the ISC software model. The client has function blocks and again an interface to talk to any server and get the information back. And then yet another interface that we use is the interface between the tools. So if you have if you have a development tool and you want to read in certain parts that has been developed by another tool, or you want to put it out to keep the source code in that sense. And that's the horizontal line. You got the vertical line where you got producers of the graphical and logical information. For the consumer, think about version control, or think about high-level tools on top, where you simulate your plant and your robot movements. And you want to have access to the code. You want to have access to the timing parts. One of the users of this one is the group Automation ML, where they focus on the production line for cars. That is just one of their focus. But it started with the production lines at Mercedes-Benz. So you got all kinds of issues there: topology, geometry, kinematics, motion planning, behavior. And you want to simulate that with all the different software tools that are there and combine them and provide this glue, what they say, between these different tools. So you can exchange the information. But in the end, Mercedes want to make cars. So you want to make sure that after all the simulation, you get your relevant information for your controllers out of your system. And with that one, you can make sure that you have a consistent system in your plans. That was the idea. So it's another interface. It's now IEC 61131-10, so not only a PLC Open standard, but also an IEC standard. And so that's a little bit of what I wanted to say about the software interfaces. Logic, motion, safety, you saw that one. We link those into one development environment, provide structuring, decomposition, reuse, and less training. So it's more what's in the head. And on top of that one, we added OPC UA and XML as interfaces, and we did a lot of training to give guidelines there. So much for me. Our tagline is for efficiency and automation. That's what we try to achieve. And the automation here is the industrial automation. That's now sometimes called OT, operation technology, versus the IT, information technology. Yep. So I hope this gives some information. I always look to ROS and to make sure that we could interface to them too. From our organization, there's no conflict whatsoever in that sense. So I think we can, if we find a good way to cooperate, let me know, and I'm open for that part. This is the website, and this is my email address. If you want to touch on me, you can download all these specifications from motion safety from the website XML. You can download them all free of charge. So if you want more specific information, okay, this is it. So I know I'm in a hardware interface group, that's how it's called, but we don't do the hardware, we focus to the software. I hope that is, I explained to you what we do there. Any questions or remarks, or do you like what we did, or have other questions?
No, I think it's pretty good. And I think one of the things we're interested in, obviously, is, I know it's hardware interface group, because we are thinking about trying to clean up some of the, like, providing guidance on how, like, people create the drivers, if you will, or the interfaces for their hardware to play with the ROS ecosystem. So in the end, but it doesn't have to be restricted to hardware, right? Other software tools want to interoperate with the ROS ecosystem as well. So hence, yeah, it's fine if it's software. So I think in general, and obviously we've done some work with OPC UA to ROS functionality as well. So there's some synergy here, right? Because you're part of OPC Foundation. But I think overall there were some really good nuggets here. Are there any questions from the audience?
Hello, good morning. Thanks for the presentation.
Okay.
I have a question to the general audience, as well as you, about IEC 61850 and the DDS that is used in ROS. So they both are published subscribe type of methodologies, and I was wondering if there has been already some work to incorporate a translator in an OPC framework.
I don't know.
Mm-hmm.
You have to ask the OPC Foundation. I don't think it is. But there's of course a difference between let's say a network where you think about moving around bits and bytes and the level that OPC UA has. OPC UA looks to the information in this case. Huh? So I asked the value of a temperature controller. I don't think in bits and bytes. I just named the temperature controller and I asked the value for it. So it's a different level. And if I know 61850, I'm not that sure, but that's really a communication protocol. So it's not so much about information, more communication. Mm-hmm. Am I correct or not? I'm not so sure about 8050, but that's this. I'll perhaps put the other way around. What is the name of 61850? How's it called, the spec?
61850, I'm not very knowledgeable in that. I know it was originated in the Europe by the electrical power industry players, and I don't think at the bottom layer it uses any of the other protocols that are typically available in the industrial domain, but it does use the publish subscribe methodology, where I believe there are topics and subscribers and publishers, just like the data distribution service used in ROS. So I thought potentially for integration between ROS2 in particular and some of these industrial devices that use 61850, that a translator could be more easily implemented between those two protocols. And I thought that could be an entry point for that integration work.
I'm not sure if there's so I'll put it the other way around. First of all, this is more an OPC foundation topic in that sense. But secondly, what you then see what's done is that you put a layer of let's say information on top of the protocol.
Yeah.
So you want to know what is on the other side. Huh? You want to be able to scan it, find all the names of all the units, of all the resources that are there, and what it can do for you, and then you want to either set some values or read some values.
Yeah.
So it is more at that level. It's more at the profile level than at a protocol level.
Yeah. Okay. Thank you.
So there's not something that PLC Open looks into. It can be something that OPC Foundation has done. And that very well can be, because they got so many profiles now up and running that you have to check their website. But then you will see it's dedicated to an industry. So the industry with the street lanterns probably needs something else than the energy production sites. Yeah?
Okay.
Good discussion. I think there is some other prior work where there was some mapping of DDS to OPCUA on a recent kind of ARM Institute project, which is a government industry collaboration institute. I can go see if I can find some of the published architecture for how they facilitated DDS, OPCUA, and MT Connect, right, all playing together. And it was an interoperability demonstration enabling diverse devices, including one ROS-I system and a ROS-2 system, plus a machine tool that was leveraging MT Connect and another machine tool that was strictly OPCUA. And there was some real interesting techniques and approaches to enable info sharing between a fully DDS-based system and OPCUA. I'll have to go see if I can pull some of that prior art and then what standards were referenced to kind of make that happen.
I think you also should check the FLC activity now in OPC Foundation, the field level control, where they do not only specify the communication to the field, that's in the long term, but also the communication between two controllers. So controller to controller is the first step that they will do. So that can be close to, they use several mechanisms for that one. So it could be interesting to check if that maps to your environment too. Look into my industry in that sense and see that, let's say, all suppliers are moving to that part.
So hi, this is this is Gijs. I'm thanks for the
very Dutch, Gijs.
It is actually.
Yeah.
I'm in Delft.
Okay. Okay.
I'm wondering, you said something about PLC Open providing basically vendor agnosticity. So it doesn't necessarily mean, it doesn't matter where your hardware comes from or your server drives or whatever, as long as the the functional interface is similar or the same, then you don't need to bother with the details as a developer. I think that's definitely something that PLC Open shares with ROS. I mean, that's one of the main advantages of using a component-based system, such as PLC Open, but also as ROS. But where these things tend to sort of fall short is in, I would say, characterizing or modeling or describing or standardizing the timing behavior. For instance, if you're talking about dynamic processes such as motion, then I'm wondering, how do you guys deal with the variability in the behavior between motion controllers? Because you mentioned something about robots, and especially the kinds of motion, synchronized motion that you showed. You really require a very sort of detailed and accurate description of the behavior in a dynamic sense of all involved axes to be able to actually synchronize these kind of motions. So in the ROS world, we have some standardization of the interface level, so the syntax and the semantics, but the semantics typically don't go much further than makes it move in a joint space way. So it's not Cartesian, it's all purely joint space motion, but it doesn't say anything about how these things will move. And the kinds of things that you just described, I believe, really require down to the millisecond level, maybe even a description of and standardization of the semantics. So when you say it's possible to sort of abstract away all the, let's say, OEM or manufacturer specific aspects of your program, I'm wondering how you deal with those differences, or are manufacturers required to implement certain behavior unless, and if they don't, then they just don't get the PLC Open sticker of approval, to say it that way.
That last one is true, but in essence, everything that we do in the PLC world is a really hard time, real time. So 250 microsecond loop times is for us a relatively normal and environment.
Yeah. But sorry for interrupting you. I understand that. I mean, we all know hard real time. Those requirements are clear. I'm more thinking about, let's say you showed an example with a KUKA robot, for instance.
Yeah.
Let's say I want to do this with if they ever implement compatibility. Let's say I want to do this with a Yaskawa or a Fanuc or an ABB or a UR. They all have their own different motion controllers, and I'm just wondering, how would you approach sort of abstracting over all of those? Because that seems to be really difficult to me, right?
It is. The current specification we work on is 2,236 pages. Nevertheless,
yes, okay, but that's not really a pragmatic solution, right?
We do not say that all these robots behave the same. They won't. Yeah, one is smaller, one is larger. They will model everything. They all will do it a little bit different in that sense. We don't make the whole world equal in that sense. Huh? So we don't model that part. If I start with one axis, even there we cannot completely tell you that it does the same. Because one of they all can improve on their internal regulators in their drives. So one will be better than the other. We cannot model that part. We don't want to model that part. For us, it's a move. Absolutely, is a move.
Where does the abstraction stop then? Because if that's not part of the standard, I would say, then the functional blocks may have the same interface, but the behavior that they elicit from the underlying hardware could definitely be different. So that seems to me like a serious limitation to the abstraction, right?
It partly is. It's depending on what you're really looking for. The good thing from the abstraction is that the look and feel of these systems are the same. Yeah. So the knowledge that people have in their head can be reused over the different systems. Yeah. That does not mean that all these systems behave the same. It will not. And we don't model the mechanics and all the joints and all the things around that parts. We don't do that. Yeah, and if one control algorithm is better than the others, the robots will not behave the same. And we don't want to mention that one. We do not specify a robot. We look to how motion is done in that sense.
But a robot is a device which offers motion, right, in a Cartesian
Yes.
or a joint space
Yes.
world. So what is specified then? And I'm not even talking about robots. Let's just think of a single drive.
What is specified, and first of all, if you want to move your TCP to a certain position or a certain path in space, yeah, then it is specified how to do that. There's a function block for it, and the inputs is you can define if you do the access system or the product system, coordinate system, which coordinate system you want to use. So what the values are, and with that one you can define a path. How well the robot will follow the path is not our issue. You can measure that. We give you the tools for that one, but we do not pre-specify that part. That's up to the user.
Okay, so the semantics that are standardized essentially go as far as saying you will roughly get the same behavior, but at least the syntax or the interfacing and the way that you program it will be the same.
Yes. Yes, and the devil is in the detail, and I know, but the issue is that there will be always differences in the different robots from the different suppliers. So that's not our world. Yeah, that's where the user specifies we want a repeatability of 0.1 millimeter. That's something they can specify. Yeah. And I know that's some of the robots won't be able to do that, and some of them will. That's not our world. We look more to how it moves. How do I specify the movement? What the repeatability is not part of our spec.
To be, what is the sort of approach that you take? Because it's very common in ROS interfaces to take sort of the lowest common denominator approach, which means that you get a very, I would say, coarse or bare specification because you want it to apply to as large a sample or section of your application domain. But I think in your case, the approach is different, right? You just specify certain things and then it's up to the implementers to adhere to those standards and say,
yes.
I do this and this, and then I get the seal of approval. I think that's the main.
And they are responsible that it runs in their environment, including their network technology, including their architectures. And as not all the networks are the same, some of them perform much higher than others. So the robot will not be the same.
Well, I'm not just thinking about robots, by the way, but yeah, okay. Okay, thanks.
Okay. I'm in Gorkum, by the way.
I like the way that the subtitles or the, what is it? Translated.
Oh yeah, that this is okay. Gorkum he doesn't recognize. Horrorcom he does. Okay.
The subtitle feature is it's probably
horrorcomedy.com. That's an interesting one. Okay.
I think there was a question by Dennis, Matt.
Oh, we did have a question on the chat. Where do you see a possibility of connecting PLC Open and ROS? Sorry, my mic is not working. That's from Dennis Stogel, who's online.
Let me see where the chat is. Where's my? Oh, why don't I see the chat? Okay, can you repeat the question?
Where do you see a possibility of connecting PLC Open and ROS?
Well, one of the issues is, of course, if I look to ROS as being the operating system for robots in that sense, I know it's more, but if I look to that part, we of course want to include ROS in the interface that we built in that sense. So if you have a separate controller running ROS and you have a separate PLC controlling the production line, it wants to talk to the robot controller. That's one. The second part is, if I include the ROS operating system into my controller, I still want to be able to talk to each other. Yeah. So that means that we need an interface there too.
Okay. What is the what's the potential process for kind of collaborating on such an interface?
If we can identify the topic and specify that one, I do normally do a call within the PLC Open members who wants to participate there. If there are sufficient respondees, we can start the working group.
Okay.
But in this case, I think they probably will want to start, because there's an overlap in the people. They want to start after we finalize this robot interface definition. Which, by the way, is implemented or will be implemented by all the robot suppliers you mentioned until now. The one you missed is universal robotics.
So this robot interface definition is kind of, so to speak, in draft at this point?
Yes, well, there is a Siemens version. And Siemens took care that it was dealt with the robot suppliers. But we do not totally agree with each other in that sense. So we'll have a meeting somewhere in November where we again, I would say, to make sure that we understand each other better. We can interface here. So we get a common interface definition.
Okay, cool. I've noted that in the notes. Any other final questions? We're kind of getting close on time. Eelco, I really appreciate you taking the time to put this together and share with our group your team's journey and your organization's journey, and in this notion of abstraction and where you draw the line as far as, like, you know, specifying or getting to, so to speak, consistent behavior. I think that's been, you know, my team's experience, that if, yeah, can we interface with different robot OEMs? We can, right? But then, like, if we say go from like a KUKA robot to an ABB robot, we will have to do some work because the behavior will be different. And so it takes further optimization to get back to the target behavior. And I guess, like, just understanding, like, the line of abstraction relative to target behavior, where is that? And then what guidance do we provide relative to what do you do to get back to desired behavior? I think that's an interesting discussion, right? So is there anything we can do to kind of help capture or provide guidance there?
If you currently look to the KUKA MX automation product, you will see that follows these what we have specified in part 4 in the coordinated motion.
Okay, that's a nice reference too.
And you can check on the function blocks, and download the spec and go through it. It gives you a feeling how we look to it.
Great. Great. I will go ahead and stop the recording. Again, thank you, everybody.